Good afternoon. I am Sunil Bhandari from Advanced Structures and Composite Center at the University of Maine. I'm here today to talk about how we used 3D printing to manufacture a culvert diffuser to be used for culvert rehabilitation. What are culvert diffusers and why are they used? Culvert diffusers are gradually flared culvert outlet sections. They are used to increase the culvert's capacity and decrease the outlet velocity. They are used where existing culverts are undersized due to the effects of climate change or land use changes. They are also used where the rehabilitation of aging culverts causes a reduction in the culvert's capacity. The current culvert retrofit technology uses slip liners. The slip liners cause a reduction in cross-section area of the culvert and hence reduce the capacity of the culvert. The culvert outlet diffusers increase the culvert capacity and compensate for the losses due to the liner retrofit. They also reduce the outlet flow velocity and minimize erosion.
By using the diffusers, the culverts can be effectively rehabilitated without reduction in the culvert discharge. Hence, the cost associated with manufacturing the new culvert, digging up the highway, removing the existing culvert, installing the new culvert, backfilling and resurfacing can be avoided by culvert rehabilitation technology. Furthermore, the highway traffic disruptions that are caused by culvert replacement can also be avoided. The diffusers improve the culvert flow, which would enable effective rehabilitation, preventing long-term highway closures to replace these 50, 60 years old culverts at tremendous costs to the traveling public.
The objectives of this project are to explore the feasibility of using large-scale 3D printing to manufacture culvert outlet diffusers with site-specific optimized designs. To design and manufacture an experimental 3D printed culvert diffuser prototype to evaluate the hydraulic capacity at the site, to assess the use of bio-based renewable polymer composites for manufacturing culvert diffusers, to explore the segmental manufacturing of 3D printed culvert diffusers, and to evaluate the performance of the 3D printed culvert diffuser in the field. So large-scale 3D printing. Why use large-scale additive manufacturing to make culvert diffusers? The geometry of the diffuser inlet needs to match the geometry of the culvert outlet. The geometry also depends on the site conditions. The geometry is non-prismatic as it is flared at the end. Unlike the culvert that it is attached to, the diffuser does not directly withstand the load from highway traffic. There might be some backfill loads if the diffuser is buried. Even polymers with low strength compared to reinforced concrete or steel can withstand the loads on the diffuser. 3D printed diffusers offer significant cost reduction to the currently used method to manufacture diffusers. On the right, you can see the large-scale 3D printer that was used for this work. The printer has a build envelope of 60 feet length, 22 feet width, and 10 feet height. Comparing large-scale versus desktop-scale 3D printing, we can see that the extrusion rates in large-scale 3D printing is much higher. The build envelope is also much bigger. Pellets are used as feedstocks in large-scale 3D printing instead of filaments, which makes retraction difficult and seams at start and end points of diffusion more prominent. There are 4 heating zones with increasing temperatures in the single screw extruder. It takes longer to heat up such large amount of polymer compared to small volumes involved in desktop scale 3D printing. The bead heights are much thicker, typically ½ inch wide and 0.2 inches high compared to desktop scale where the largest beads are 0.8 millimeter wide and 0.4 millimeter high. The low surface area to volume ratio of the beads makes the beads retain heat much longer. The minimum layer time which is the time required for the layer to cool down and become rigid enough to support the layer above it, is much higher in large-scale 3D printing. In small-scale 3D printing, it is rarely an issue. On the other hand, the maximum layer time is the time before which the new layer must be deposited so that the layer below it is hot enough to bond properly. Layer time in large-scale 3D printing is bounded by these maximum and minimum layer times. The geometry of the diffuser is shown on the figure to the right. The diffuser is 8.5 feet long. The circular end connects to the culvert that is 15 inches in diameter. The diffuser flares up to an elliptical shape over a length of 72 inches to a measured diameter of 30 inches on the flared end. As you can see, this is a non-prismatic shape, and such shapes are difficult to extrude using a die. This geometry is unique to the Thorndike Culvert diffuser. We adopted a segmental construction approach to manufacture the part. Instead of printing the 102-inch part, we divided it into 4 segments and printed the 4 segments. It was done to maximize the use of layer time. Layer time is the time taken to deposit one layer of material. In large-scale 3D printing, a layer needs to cool down sufficiently so that it becomes rigid enough to support the layer above it. Dividing the part into 4 segments would allow to deposit 4 times as much material in a given layer time. Also, segmental construction would allow us to build parts that are larger than the build envelope of the 3D printer. The start and stop points in the extrusion create seams, which are points of weakness in the structure. To minimize the seams by creating a continuous deposition path, the 4 segments were joined by walls as shown in the figure to the right.
Material selection. PLA wood was the material selected for this project. The Thorndike diffuser is experimental and not permanent. It will be installed during the dry season in July, and water flows will be measured in late October. Then this diffuser will be removed from the site. We plan to study the durability of the material in the field and the degradation in the material properties of the material after exposure to the field conditions. The biodegradable material can be easily disposed after the project is over. The PLA wood material has sufficient mechanical properties to withstand the loads to the diffuser. For structures that are exposed to the environment for long term, a non-biodegradable polymer system would be more suitable. We plan to use ASA wood fiber or other durable thermoplastic composites for permanent installations. The choice of polymers also depends on the surface finish necessary for the project. As you can see on the figure to the right, different surface finishes can be created for the wood PLA material. For this project, however, the as-printed surface without any further processing was considered acceptable. The print setup is shown in the figure to the right. The vacuum line over the base creates suction to hold the 3D printed part in place. Hot air is used to reheat the previous layer to enhance bonding. The extrusion temperature of 207 degrees Celsius and the layer time of 4 minutes 45 seconds was adopted based on previous trials. A bead width of ½ inch and a layer height of 0.2 inches were adopted. The extrusion rate was about 50 pounds per hour for this print. So the total printing time for this part was 8 hours and 41 minutes. The weight of the part was 410 pounds as printed. The surface roughness was considered acceptable, except at the seams. The seams are the start and end points of the extrusion path. Cutting and joining operations were carried out as post-processing operations.
trial and error and the lessons learned. Two trials were done to determine the suitable layer time and suitable geometry for the part. At first, the layer time was 2 minutes 30 seconds, and the material did not cool down enough to support the layer above it. As you can see on the figure to the right, the layer collapsed as the softened material could not support the weight of the layer above it. A higher layer time allowed for sufficient cool down of the material. The determination of layer time is based on trial and error right now, but we are developing numerical models to calculate a suitable layer time for the 3D printed part. The extrusion temperature was increased from 200 degrees Celsius to 207 degrees Celsius to get a much smoother surface. Walls joining the segments were added to provide a continuous path for material deposition and to minimize the seams. Post-processing cutting. Cutting PLA wood was especially difficult since PLA softens and melts at relatively low temperatures. Heat generated during cutting softened PLA and the material stuck with the cutting blades. This caused some problems during cutting. Such problems were not observed while cutting ABS carbon or other polymers. Uh, Electric saws and routers were not suitable for cutting this material. Handheld saws with slow cutting speed that generated low heat were more suitable. Post-processing plugging holes. Holes and rough surfaces were created at seams. The seams are the start and stop points of extrusion path, and the holes created needed to be filled. We filled the holes with plyo-grip polyurethane adhesive and let it cure. The segments were joined with ply-grip 7770 urethane adhesive. The joining surface was lightly sanded and cleaned with isopropyl alcohol. Ply-grip 7770 adhesive, which has a longer curing time compared to other urethane adhesives, was applied to the surfaces and aligned one segment at a time. The joint part was allowed to cure and set. Conclusions. We successfully manufactured an 8.5 feet long, 2.5 feet wide Culvert diffuser using large-scale additive manufacturing of PLA wood. Segmental manufacturing of long and narrow parts enables faster manufacturing times. Post-processing, especially cutting low-temp softening polymers like PLA wood, needs further investigation. Optimized design of Culvert diffusers based on site-specific hydraulic condition can be manufactured using large-scale 3D printing at lower cost than other current methods. Hydraulic performance in the field as well as ease of installation and durability have to be demonstrated for technology transfer. For larger diffusers, there is a potential for even higher cost savings as we could fully utilize the high extrusion rates of 150 pounds per hour that is available with the Maine 3D printer. For this part, we could only use 1/3 of the maximum extrusion rate possible due to the layer time limitations. The research work has huge potential for developing a more cost-effective diffuser that could lead to commercialization. The segmental manufacturing approach adopted in this research would aid the commercialization since large-scale 3D printers that are smaller than the ones available at UMaine, that are more commonly available and more geared toward production than research, could be used to 3D print smaller segments, which could then be joined to create the larger part. Future work. The diffuser will be installed in dry season in July of this year. Performance of the diffuser will be evaluated by measuring water flow during rains in late October. Performance will be compared with the fiberglass diffuser. If the performance of the diffuser is acceptable, larger culvert diffusers will be manufactured using segmental construction and tested.
So now is the time for questions.